All right. Well, thanks for showing up, everybody. Excited to kind of get into what I've been up to these past couple of years. I'm going to start just kind of like with a brief overview of like the couple projects that I've been working on. The first one is the kind of optimization on for derivation production. Um, limiting basket buffer limits, and I'm going to go over like what everything means later on. But just to give a brief overview, the first project, was a qualification task for Atlas. It was written into an internal note and shared, and I was lucky enough to go to Oslo and present it at the Software and Computing Week in June, and it was a lot of fun. Learned a lot. The second project was more of a modernizing of current tests that exist within a code base known as Athena. Um, and there was some additional features that were needing to be tested for nightly builds, and that was just recently this past week merged into the code base. Um, yeah, so with that, I'm going to get into a little bit of just like some things. So for people who aren't exactly working on LHC stuff, um, so there's a lot of overlap between the LHC and like Atlas experiment work and like Dune. But one thing they all kind of share in common is we need a lot of data. And so each of these you know topics are going to be needing as much data as possible. And so specifically the Atlas experiment, though, talking a little bit about that, it's the largest general purpose detector for particle collision. It's 46 meters long, 25 meters high and wide. It's a very large collaboration. Um, the inner detector measures direction, momentum, charge of electrically charged particles. The calorimeter surrounds it absorbs most of the particles except for muons and neutrinos coming from those collisions, those proton-proton collisions, forcing a stop. And then the muon spectrometer identifies and measures the momenta of muons. On the computational side of things, analysis needs a lot of compute and storage. The detector itself stores about 1 to 2 megabytes per raw event. And there's 40 million beam crossings per second. So that's like, I think it's around a million gigabytes, like a petabyte of raw data per second. And it's really expensive to hold on to that stuff. So you have to be able to scale that down. So both data, raw data and Monte Carlo simulation both go through this kind of reconstruction of hits, and that's where you get that like order of a megabyte per raw event file size. But what we're worried about for this first project is really like the derivation process. So bringing that 1 megabyte down to about 10 kilobytes, tens of kilobytes per event. And that helps bring down how much is permanently stored down quite significantly. Um, so just to give a background on like the files themselves, um, so after reconstruction, we get this analysis object data, so AOD, um, and that's where you get the 1 to 2 megabyte per event file size. And then the derivation production job itself brings that down and compresses things to something smaller, and that's what's called a derived analysis object data, so DAOD. It's a root file used for analysis. There's two types with Atlas. It's the Fizz and Fizzlite. And grid computing is used for these to create these files in a job. And that can be resource intensive with high memory usage, and again, disk space is limited. So you you want to try your best and just, you know, consolidate that as much as possible. And each of these derivation production jobs need to fit into a 2 GB per CPU core budget. So we're also limited in how much memory is available for a given job. Um, so how are they organized? DAODs have T trees, um, and T trees have branches, which are um, they have dedicated memory buffers that store data. And once those buffers are compressed, they become baskets. And these baskets can have like a limited size, and by default, it's 128 kilobytes, um, and a minimum number of entries. Um, so that's some two conditions that they require. And you know, the question to ask is like, what are some ways we can reduce the usage on to the grid? I think in the future we have like plans to move into R and tuple, but that's still kind of R&D. So for now, like what we were thinking was, could we try limiting the basket size and playing with that minimum number of entries per basket? So that's what we started to look at. Diverting attention to kind of more root and Athena for a moment. Athena is the open source software framework for Atlas. So when code is changed, it uses CMake to build the entire Athena package. Python is used for configuring the jobs and giving them options. And C++ is used for more of the algorithms and framework for each of the, like how you define an object and manipulate it with root. Athena works with root for both reconstruction and derivation. Currently, root and Athena for the derivation job itself limit the basket size to 128 kilobytes, but that's after memory allocation for the job. So one question would be like, what happens to the memory usage in disk space if we kind of play with root and Athena before the actual job is being executed? Initially, the kind of early tests, we modified both root and Athena to see like what would change, but it became clear that root, when we hard coded the basket limit in root, it wasn't going to be as beneficial as if we just focused on Athena. So we just kind of left root alone as much as we could, and we just focused on seeing what Athena is doing and how those derivation jobs can be better optimized. If we, there's the second condition aside from the other, like the basket size limit, is the minimum number of entries in the buffer. The way I kind of think about it is like if each buffer has a minimum of 10 entries, then we can fit all of those entries into the buffer. But if at the end of the job there's one buffer left and it has like 4 entries, it'll just be flushed to disk anyway. Yeah, and so once we start running the derivation jobs, we're going to look at like the presence and omission of both the basket limit and the minimum number of entries. And so of course the default is that they're both present, but what we're going to be seeing, and I don't have a pointer here, but the top table shows us the data derivations, and on the left of that you'll see the max PSS. That's the proportional set size, and that tells us how much memory is being used throughout the duration of the job. And the output file size is how much is going to be stored at disk. So Data derivation jobs see little effect. You see like plus 2.5% when the minimum number of entries is gone. Um, so that's, I mean, that's an increase in memory usage for not as much of an effect with the output file size. So um, when we look at instead the Monte Carlo derivation, we see a much larger effect. So without the minimum number of entries, we see an increased memory usage, but a decrease in overall output file size. Um, with the minimum number of entries and without basket limit, there's a minimum change in the memory, but an increase in the overall output file size. So um, when both are implemented, just so happens that they cancel each other out, and we're hitting a balance that's not increased memory usage, but also not seeing the full benefit of a decreased output file size. Um, so for now, it's worthwhile just to keep both. Um, but the next question could be like, well, how good is that 128 kilobyte basket limit? So we go higher or lower? Um, an earlier kind of toy model that we used to kind of decide whether or not to like look into this was, excuse me, if we decrease the basket size, we wouldn't see as great compression. But if we kept increasing it, eventually we wouldn't see as much of a we wouldn't see as much of a beneficial to return. So lower basket size would give us less compression, and then that would give us a bigger file size in the end. So we definitely don't want to go lower. But if we went higher, what really happens with the Monte Carlo derivation? Because that's going to show us a more exaggerated effect. So what we saw was, yes, we're going to see like increased memory usage, but um, if we got rid of it entirely, we'll end up seeing the full extent of how much we're saving in like our Fizzlight output file size. And that's where we see like, so and under the no limit, we see an increase of 11% RAM memory usage and a decrease in like 5.5% output file size. So um, that's a trade-off that was discussed. Like, is that something we're like willing to make? But I think the consensus was like the balance is good enough for now. Um, Another kind of aspect to this project was looking at the branches themselves as we were messing with the basket limit. Um, some of them show um, we specifically see a more, and this is consistent all around the Fizzlight simulated data sees this kind of greater effect. Um, this HLT nav summary on the top, it's the maximum basket size set by root. Um, so we're not really sure why that happens, but this is what I mean. You don't really see as much of a good enough compression, but it's still a large branch. Um, um, yeah, the basket size doesn't really improve beyond 128 kilobytes. These larger branches on the bottom, they have these really high compression to, so it's like um, the ratio of like the total file size before derivation to after derivation ratios. So that tells us that a lot of like repeated values, like zeros, are saved in the AODs. So like So that, I mean, larger file sizes before derivation could tell us like they're being generated in simulation in a weird way. So that was something that was brought up after the int note was kind of put out. So and there was these are just cherry picked hand few branches that had high compression. There were some others around like the 30-40 range, but these like 90 and 74 compression ratio branches were something that we wanted to kind of call attention to. Let's see. So, and
I have a
that pretty
quick
much,
question.
sure.
For the last slide, are these all the same data type, these branches?
Data type how? So they're all root files. They're all like branches that come from a root, like the
I just
same.
meant for like the values themselves, are like they all like ints, 32s, or is it mixed type?
I think they're all the same. Um, I'm not entirely sure because I think they're all saved in different ways. So like the tracks can be saved as,
The links are
yeah, I
just
think.
pointers, right, to other things.
Mhm.
And the
Right, the
decision,
links are what is called the element links. It's essentially just an index and the name of the container that it points to. Decisions are essentially unsigned integers. It's a vector of doubly nested vector of unsigned integers.
Mhm.
Okay, yeah, because I was curious if the data type or the type of object had an effect on this compression.
Mhm.
Thank you.
Yeah, I imagine it does. And I think that's like what we, so, I mean, with the compression of 93, I think the expectation was it was a lot of zeros that weren't needed. But I don't remember what the kind of end result of that discussion was.
Yeah, we know there are many links in there that are not set because they have no partner to be linked to. So those links are zero and they compress away, and that's why you get this high compression.
Mhm. Okay. Yeah, so just to kind of cap off that project, the basket size limits are currently in a good state. There's opportunity to save disk space, but at the expense of memory usage, which isn't obviously going to be beneficial with that 2 GB per core kind of budget per job. But the balance is good for now. And again, like those highly compressible branches were something we wanted to kind of call attention to and leave to the experts to kind of decide what should be done with them. But it was interesting nonetheless. The so the second project was modernizing these like IO the input output continuous integration tests for um, Athena itself. So with the kind of latest additions to Athena, and we want to make sure that everything that's going to kind of help the high luminosity era of the LHC is going to be well tested and kind of robust when it comes to integrating new code into the framework. So the unit tests themselves are tests that test the core functionality of the IO framework. So if one of these other softwares that exist that are being updated continuously alongside Athena end up breaking one of those core functionality, like the unit tests will catch that. So that's something that we want to make sure is always being updated to the current standard, I guess. One of the new additions to Athena is this XAOD is what it's called, EDM. It's similar to like just an AOD, but it's a little bit different. I'll get into it in a minute. But an event data model itself is supposed to be like a collection of classes, and it's kind of like a standard with the goal to make things easier to use and manipulate as a developer or when doing analysis. So think of it like a standard, and it's specifically just representing particles in memory and or different physics objects in memory, and how they're stored at disk and manipulated in analysis. So their relationship to each other is kind of what that EDM is. So again, like it makes things easier for developers and people doing analysis. There's like a commonality in the code across the detector subsystems and reconstruction and analysis groups. There's more use of common software, which is good for like readability and debugging. So that's really a core motivation to have an EDM. The previous one had like a transient kind of present in memory, and it would have info attached to it, and eventually it would have to be converted into something that would be stored persistently, so long term into a disk. The problem with it is root couldn't, the way I understand it is root couldn't handle it. There's the way it was, the inheritance was kind of structured. It was a little too complex to be held in memory by root. And that process of conversion from transient to persistent was an extra step that could be cut out. And these are some of the things that were implemented into the XAOD EDM. And XAOD I could be wrong with it. I don't think it really stands for, the X itself doesn't really stand for much, except that it's newer AOD. But itself, there's some like design requirements. So it has to be lightweight. It has to be kind of easy to pick up. It reads and writes fast. So Athena and root can use it and write it fast, and it can be flexible. You can add and remove variables at runtime, which are known as decorations. And these were all things that we were going to try and test for this unit test itself. So when we wanted to create a unit test for the XAOD EDM, it was worthwhile to create an object. I guess an example electron is what we called it. And we try to make it as simple as possible. So this electron has like a PT, a momentum, and a charge. And we were able to kind of call back existing objects that already have a momentum and convert that from like the transient persistent EDM to an XAOD EDM. So this structure is kind of how it would look like. You have header files, you have interface objects, but they don't hold on to persistent data. That goes to the auxiliary objects that kind of serve for the interface objects. And it makes things a little bit easier as a developer just to call like an example electron or a container of electrons. And it works with unique IDs to help identify where that data is being stored. Yep, and we need data vectors specifically to create like containers of multiple example electrons. And also during this process, yes, we can add dynamic variables to the objects, and it'll be able to read and write them when we want to. Yeah. So how we can test them again, there are ways to test them with job options. So that's where Python kind of defines the input and output files, and like what algorithms to call. And you can also define like which objects in those input files can be written out again. You can define which decorations you want to include or not. And each of these unit tests will run the job and then create a log file that will be compared to a reference file that's been run before. And if it's off at all, then the unit test will not pass. Yeah. Okay. So the way this one works, that we worked with, Athena pool example, it has a host of different tests, ones that read and rewrite. But the one that I really kind of worked on was just the example electron, where we read and write that. So that specifically, I'll go into that in a little bit, but specifically when you run these tests, it's usually done through CMake, and it'll have all these tests kind of run down, and they're pretty fast. They only take like 5 to 10 seconds to really run through. So because they're only supposed to be unit tests, they're not like whole derivation jobs, which can take hours. And so looking at the tests that I wrote specifically, we kind of start up at the top with the example track, which is created from another unit test. So we can take that object, read it in using an algorithm. That algorithm will then kind of give it off to another algorithm called write example electron. And you just write the same PTs together, and it'll then save that example electron to a file. Yep, and so that's what's sent to disk. So reading it back, you take that file that was already generated, and you can just read through each of the example electrons and what their PTs are, and make sure that's all aligned, and that they're all the same. And that should be, and if it's off at all, like the CI tests will catch that. And that should really be it for that. These are the actual algorithms themselves. It's just saying like, yeah, take in each of the example tracks, get their PTs, save that into an example electron. And additionally, you can, set your decorations to some whatever you'd like, to just keep consistent. And then again, you can read it back and just verify if it's all aligned. But yeah. Yeah, when it's all kind of said and done, you can create a merge request for in like GitLab. You can iterate through and make sure that these tests are working, and figure out why they're not. I think mostly the issues that I would have with these would just be the log files would have different UIDs for the different objects. the values themselves, the PT would never change. It would just be how they're saved. So it's very strange, but it's a useful debugging tool. Yeah, again, these is just you run the script and it compares the log file that you run with the reference file. Yep, the unique identifier is kind of associated to each of the XAOD objects. So, and eventually you try enough of these, and eventually, like the unit test will pass, and it will kind of come back like that. And just to kind of wrap that up, they were, these sets of tests were added in and merged last week, but it was kind of a steep learning curve trying to learn the difference between, well, really how to write these objects to begin with, let alone testing them. Yeah, I think that's pretty much it. Yeah, I think yeah, okay, cool. Any questions?
Thanks, Jack.
Yes.
That was great. Yeah. Do anybody have any questions about cats or otherwise? Yeah, Hector, why don't you go ahead?
Hi, Jack. I have a question on going back to the way that you create the electrons. So the numbers that you use to create the electrons, are these hard coded in the, like, are these always the same and hard coded on the files, or is this something that you can input from the outside, or via some kind of configuration file or something like that? Or they are always exactly the same?
So do you mean are you talking about the UIDs for the objects or the
So you
PT?
create some objects, right? But you create
Yeah.
them with some information, and then you cross check in the outside, like on the reading part of the test.
Right.
So are the electrons always exactly the same? Like, are you hard coding the values and the things that go into the electrons, or are those, are those modifiable somehow?
I think you can modify them, but the way that these tests are kind of ordered, what I'm pulling from is, or where you get the PT from, is this like example track object, which we can hard code, but like other tests have already given them. It's supposed to be an example, so you can hard code in something relative to an index of which example track you're talking about, or something like that.
But the way that you are doing it now, these are always the same electrons whenever you run the thing.
Yeah.
So they are in some sense hard coded. I mean, well, not hard coded, but they're but then where are they coming from? So you're writing this example tracks and example electron just from some numbers that are coming from somewhere, right? My question is really, like, are these numbers just something that you have written in the same file, or are these coming from some previous step, or that was sort of the question?
Yeah, I think for these tracks, these are just dummy tracks. The values are actually hard coded.
Okay.
So there's an upstream test that has hard coded values that writes out tracks, dummy tracks, and then Jack's test essentially just passes through those values to the electron PT. But yes, they're hard coded in an upstream test.
Okay. But in principle, you can take them from some, like, the idea is that you would take them from some file or something.
Yeah.
Eventually, I guess. Okay. Okay. Thank you.
I mean, I think, Hector, the expectation is that if these tests fail, they're not going to fail and return a PT that's off by 1 GeV. They're going to fail and fail more spectacularly than that, right? So,
well, sure, but having some kind of randomization on the, like, this is always the question with the test data.
Yeah,
If
yeah.
your test data is always the same, you may be unlucky and may not be testing all of the possible things. So.
Sure. Yes. You have to be careful then that if you randomize things that you're not changing the output log file.
Yeah, of course.
Yeah.
But
Yeah.
I was just wondering where, like, if this was just some kind of, for now, some small test data you were using for this.
Yeah. They're very small
And-
tests. Yeah. They're not large.
I think it's supposed to be, because we're only testing to see if the core functionality breaks or not.
Yeah, okay. Makes sense.
Good question. Other questions from people? So I'll ask you one, Jack, if no one else has a question.
Mhm.
But so if you go back to the first part of your talk, maybe you sort of said it and I sort of missed it, but can you comment on why changing the basket sizes will change the compression? Is that obvious?
Well, I think the so I think the early tests were kind of produced to mimic what we would see in real data. So we filled branches up with, and this is where like just kind of randomize like some ratio of like random values, random integers or random floats to highly compressed, like repeated integers, like 1111. And creating that mixed bag allows us to mimic data in that way. So if we then took those branches and then modified the basket limit, if we lowered the basket sizes, we wouldn't get as much compression, which means that we would be left with more data in the DAOD. So if we were able to compress it more, then the DAOD would be smaller.
But I think my
so-
question is more, what is the sort of motive, even in the toy model, whether the toy model or the real model, why does the toy model predict that you get, order 5% more compression if you go from 32K to 128K basket size? So what is it about having the larger basket size that lets compress the data better, or compress the file or that basket, that branch better?
I think it's just has to do with how it well, so if we take the no limit case, you have to access a bigger basket and hold on to that in memory. So the memory usage is going to go up. But if you have smaller baskets, I mean, you're not going to need to hold all that much into memory.
Yeah, I get that from memory. It's more the disk space that I'm
the
curious.
disk space. Yeah, I know we talked about this. I'm not entirely
I think
positive.
it's just a matter of being able to optimize the compression a little better the more data you have, right? I think it's nothing more than that. You see more patterns repeating and that sort of thing, right? I think it's common for compression.
Yeah, and so when you can compress it more,
I mean, if you think of the limit of 1 byte, you're not going to be able to compress it at all, right? Because it is what it is. And 2, you really don't have any patterns. So the more data you have, the more patterns you can find. I think that's all it comes down to.
Yeah.
More repeatable patterns that compress better. So, okay. Any other questions from anyone? So if not, thanks a lot, Jack. That was super. I hope everyone else that was super great and useful, and hopefully useful for you too. And so we'll stop the recording in a moment, and then we'll send these to Mike to post, and a reminder that we will have our next meeting in just under a month. So thanks a lot again, Jack. Thanks everyone for connecting. We'll speak to you all soon. Bye-bye.
Bye.
Thanks.
Thank you.
Goodbye.
Bye-bye.
Thanks, Jack.
Thank you. Bye-bye.
Thank you, Jack.
Bye.